in this research, we, as I mentioned, since we are focusing on the data-free pin, so we don't use data loss count. We only use physics loss count. And here is a comparison between the data-free pins and traditional numerical methods like finite difference method. Since time is limited, I would like to focus on the last item here, the source of the error. Since we always use the discrete grid point in the traditional method, so we always suffer from the discretization error, which causes numerical dispersion. In contrast, pins do not use such grid points, so it's free from this kind of error. I'm sorry, this kind of error. So pin can be expected to give more accurate results. This kind of characteristics is already demonstrated by the Raisi in 2019. This slide shows the result of our reproduction test, where pin is used to solve this kind of Vargas equation. And as you can see, there is not much difference between the CFD result with pin results when the solution is smooth like this. But when the solution becomes has a steep change like this, then the difference becomes more significant. Here is the magnified view around the region near the steep change. As you can see, in the FDM solution, we can observe the oscillation near the steep region. In contrast, in the pin solution, we do not observe such oscillation. So this indicates the potential advantage of using pin to solve nonlinear equation. So we apply this pin to solve Navier-Stokes equation. Here is an example of our result. We apply pin to solve two-dimensional Navier-Stokes incompressible Navier-Stokes equation, and we solve the flow around the cylinder, right? And Reynolds number is taken 20, 40, and 60 in this example. And on the left-hand side, we show the result from the CFD result, CFD based on the finite difference method. On the right-hand side, we show the result from the pin prediction. As you can see, when the Reynolds number is low, like 20 or 40, there is not significant difference between FDM and pin. This means pin prediction is can be said it's as accurate as CFD result. But in contrast, when the Reynolds number is higher, like Reynolds number 60, CFD predicts unsteady flow behavior and Kalman vortex shading like this. But pin failed to predict such unsteady behavior. So we started to identify, to seek for the reason why this failure happened. And in order to identify the reasons, we tried several things. But first, we checked the optimal, seek for the optimal hyperparameters in the optimization process of the neural network. And we increase as much as possible in the number of layers and also in the number of neurons per layer like this. And but as we increase the number of layers or numbers of neurons, then we observe the loss function can be reduced. But we could not further increase the number of layers of neurons since the GPU, the memory amount of GPU is limited. And also we applied what is called transfer learning. Since we found it's unstable to train the pin at high Reynolds number, like Reynolds number 60 from the scratch. So we instead of training pin from the scratch. We use the result of the pin training at lower Reynolds number, like Reynolds number 40, to start the training for Reynolds number 6. And then we succeeded to train the neural network for higher Reynolds number. And also, as already I have already shown, the results, prediction results for unsteady flow is not sufficient. So we tested different causes. That is the number of collocation points. Here is an example of the distribution of collocation points used in the training of pin. And red point shows the collocation points where the residual of the Navier-Stokes equation evaluated. And orange also the collocation points where the residual of Navier-Stokes equation evaluated. So we used more collocation points, especially near the cylinder. And also we use blue points and green points in order to satisfy the boundary condition of the problem. And also we have to we changed the time interval over which pins are trained. We started from the time interval of 100, and since we observed the pin training failed at this long time range training, so we decreased the number of time intervals down to 1, and then compare the result. Here is the comparison result for such training. The top result shows the CFD initial condition taken from the CFD, and the second figure shows the prediction result using CFD, and bottom 3 shows the prediction result of pin, which is trained with different time interval. As you can see, time interval is long, then the pin prediction looks like very diffusive solution. But time interval is short, then pin prediction comes as much accurate as CFD prediction. So these results indicate that pin, in order to accurately train pin, we need very many collocation points to train. So, but as I mentioned, increasing the number of collocation points meets the limitation of GPU memory. So we parallelized our training code using the data parallelism of the pin training. Of course, we want to try to use domain decomposition approach instead of data parallelism, but it's more difficult for us. So we chose data parallelism for the first try. And the procedure of our parallelization is listed here, but since time is limited, I would like to omit the we just use several compute nodes. And we distribute the collocation point into several compute nodes, and those collocation points are used in each of the neural networks on each compute node. And then those neural networks trained on each GPU is finally synchronized to form a single neural network. And here is the test results for our parallelized training code. We applied our parallelized code to the advection problem, as shown here. We solved this kind of advection problem, and we use volume of fluid function to be advection. And yeah, in this test, we check the strong scaling test, strong scaling and weak scaling of our parallelized code. And the first result is the strong scaling test. The left-hand side shows the time decrease as the number of GPU increase. And the right-hand side shows the relative error when the number of GPU vary. And from here, we can see the elapsed time can be decreased while keeping the relative error in the strong state. And here is another, here is the result for weak state. And here, again, the time, computational time can be kept constant while the relative error can be decreased. So we, this is the, this shows the validity of a parallelized code. So we apply our parallelized code again to the problem of the two-dimensional flow over cylinder. And then we could increase the time interval for the simulation. In the previous case, we only simulate one second for the vortex shading. But now, since code is parallel, we could simulate 4 seconds with 8 GP. And then finally, we could successfully reproduce a single cycle of vortex shading. Yeah, this is the final result of my presentation. And here is a summary of our research. Since time is limited, I'd like to thank you very much for your listening.
Yeah, thank you.